Good morning everyone. So today we are going to discuss tutorial sheet 5 which is based on Eulerian and Hamiltonian graphs. So first problem says that let G be a simple graph having two components and each of the component is Eulerian. Now what would be the minimum number of the edges that should be added to G so that G is simple as well as Eulerian. So its component are Eulerian, but G is not Eulerian because G is not connected. So we have to add a few number of the edges so that the graph becomes connected. It should remain simple and it should be Eulerian. So to address this problem, if you try by yourself, then there is a high possibility that you miss one of the cases. Actually, there are two cases. So let's see the answer. So case 1 is when both components are complete. So this is the case which has high probability that you may miss. So for example, let's consider K5. So if you consider K5, it is Eulerian, and K3, it is also Eulerian. If I have to add the edges, I can start with any vertex and connect it to the other component. Now its degree becomes 5, its degree becomes 3. I can make the degree even at a particular point of at one point of time. So I can make this one even and this becomes 6. This is 3 and this is 3. So to make it Eulerian, all the vertices should have even degree. So I can again connect them. And this would become 6, this becomes 4 and this becomes 4. And you can see that all the vertices have even degree. Therefore, the graph is Eulerian. Now, when you see the second case, then you will see why there is a possibility to miss the first case. So, second case says that at most one component is complete, because here both the components were complete in case 1. So, let's say the other case is like this, or you can have two C4s or one C6, one C4, whichever you want. The good point here is that that when one of the component is not complete, then internally you can add the edges, and when you internally add the edges, then it increases the degree of two vertices. For example, you make it adjacent and you make it adjacent, its degree becomes 4, it's Eulerian. But in the previous case, to make these degrees even, we have to introduce two more edges. In this case, you can introduce only one edge, and by adding it, its degree is 4, its degree is 4, and you can say the graph becomes Eulerian. Therefore, both the cases are important. So in this case too, minimum 3 edges need to be added to make it Eulerian, but in case 1, 4 edges need to be added. And this is why I gave a hint that discuss all the possibilities. The next question says that assume that graph G is Eulerian. You need to prove or disprove the following statement. To prove it, you need to give a justification. To disprove, you need to produce a counterexample. So first statement says that G is Eulerian as well as bipartite. Then it must have the even number of edges. Think over it. If false, give a counterexample. If true, why? Now the graph is bipartite, it must have two partite sets. And now in case of bipartite graph, an important observation is, which we have discussed earlier also, that each edge has one endpoint in one partite set and the other endpoint in the other partite set, and therefore the degree sum of both the partite set is always equal. And now the graph is Eulerian, it means that all the vertices have even degree. So this degree sum is, let's say, k, which is E1. Then this degree sum is also k, which is E1. And the total degree sum is 2k, which is twice the number of the edges, which means k must be the number of edges, which is E1, and therefore the result is true. If G has an even number of vertices, then it has an even number of edges. Again, think, is it true or not? So it's false. Let me give a counter example. Even after getting the answer that it's false, please try to produce the counter example by yourself. So this is one of the counter example. You can see the graph is Eulerian because all the vertices have even degree. Now the number of the vertices are 6, 1, 2, 3, 4, 5, 6, but the number of edges are 7, 4 in C4, 3 in C3. So you can see that it may not have the even number of edges, and result is false. If it has two edges E and F, Eulerian graph sharing a vertex, then E and F must appear consecutively. Again, it's false, and we can use the same counter example. So let's say this is E, this is F. So both the edges, they are sharing a vertex, this vertex. But now I can try to draw the Eulerian circuit as follows. So first forms C4. So I started with F, and you can see that E is not coming consecutively. There are many ways, but this one is very easy to produce, that it is not true that these two edges should appear consecutively because there is a cycle. So it depends how you follow the cycle. They can come consecutively, they may not come. For what values of m and n does the complete bipartite graph contain an Euler circuit? Which means when the complete bipartite graph is Eulerian, so if all the vertices have even degree, then of course it is Eulerian. Determine the length of longest path and longest cycle in complete bipartite graph. So this one is interesting. Just to demonstrate, let us assume that we have K23. I can number them. Now for the longest path, I should start from the larger partite set. So I should start with 3. So from 3 I can go to 1, 1 to 4, 4 to 2, and 2 to 5. So 4 edges are involved, it means the length is 4. And you can verify by yourself, this is the longest path with length 4. Similarly, if you think of a cycle, then I can start with 1, go to 4, then 2, then 5, and I have to reach back to 1. So again the length is 4. It means that it is twice the minimum of m comma n. So minimum of m comma n is 2. This means the length of the longest path is 4 and the length of longest cycle is 4. Next, construct a non-Hamiltonian graph on n vertices with C n minus 1 2, which is n minus 1 n minus 2 by 2 plus 1 edges. So in this particular case, the answer is already there in the question. If you read it carefully, you just need to identify the graph having n minus 1 n minus 2 by 2 edges. So it is k n minus 1. So consider any graph. Let's say you want to construct for n is equal to 6. So consider k5. And once you have k5, then introduce the new vertex and make it adjacent to one of the vertex. This gives you a graph with n minus 1 n minus 2 by 2 plus 1 edges, but at the same time you can see it's not Eulerian because this edge cannot be part of a Hamiltonian cycle. So the graph is not Hamiltonian, sorry. The next one is construct a non-Hamiltonian graph on n vertices that has minimum of n by 2 minus 1 degree. Now to construct this one, there could be multiple answers. I am showing you one of them. So the idea here is that, for example, let's say that n is equal to 7. So you consider the complete graph G1 of order 7 by 2, which is 4, which means K4, and G2 of order, in this case, 3. Now fix a vertex V in G1 and make it adjacent to all other vertices. Since again there is a cut vertex, so you have to visit it twice, and therefore Hamiltonian cycle is not possible. Graph is not Hamiltonian. At the same time, you can observe here is that the minimum degree is always 3, which is 4 minus 1. Prove or disprove Peterson graph is Hamiltonian. I have already drawn the Peterson graph. Now first see some properties of the Peterson graph. The first one is it has 10 vertices. The other one is it has 15 edges. And the last one, which is a concept of girth. Girth means the smallest cycle in the graph, the length of the smallest cycle in the graph, which is 5. For example, there. So you can try by yourself that girth of the Peterson graph is 5. Now we have to prove or disprove. We are going to disprove it, which means we will show it is not Hamiltonian. We will prove it by contradiction. So let's assume that it's Hamiltonian. It means that it must have a Hamiltonian cycle. Now Hamiltonian cycle means it must have a cycle of length 10, which looks like this. Now 10 vertices are already involved in this Hamiltonian cycle, and it has 10 edges, but the Hamiltonian graph has 15 edges. It means 5 more edges need to be introduced in such a way that the girth should remain 5. Yes, so if you try to add them, I have just shown you one way, but whatever way you try, you will see that 4 edges can be added in such a way that the girth remains 5. But when you try to add the 5th edge, then it forms a cycle of length less than 5, which is a contradiction because the Peterson graph should have the girth 5. So we reach to a contradiction, and therefore we can say the graph is not Hamiltonian. So this is a very interesting approach which we have used in this question, which follows and which is based on the properties of the Peterson graph. So sometimes we may not have to use some existing result to prove the required result, but we can have some properties which get violated if the graph holds some certain properties. This one is again very interesting. It says that the complete bipartite graph k n comma n has n factorial n minus 1 factorial by 2 Hamiltonian cycles. How you are going to prove this one? Or question could be compute the number of the Hamiltonian cycles in k n comma n or k 5 comma 5, something like this. So to understand the proof, let's assume k 3 3. Now if I have to form a Hamiltonian cycle, I need to start with any of the vertex. I have to go to all the vertices and reach back to 1. So from 1 I have to go to the other set. There are 3 choices. Let's say I go to 4. So there are 3 choices. Then for the other set from 4 I have to go to the same set to which 1 belongs. So there are 2 choices there. Then from 2 there are 2 choices, so 3 cross 2. So let's say I go to 6. Then from 6 there is only one choice, 2 cross 1. And from 3 there is only one choice. So it means 3 factorial multiplied by 2 factorial. Yes, again try to understand. From 1 there are 3 choices, then 2 choices, then 1 choices to visit to the other set. And to visit the same set, there are initially 2 choices, and once a vertex is visited, there is only one choice. So therefore 3 factorial multiplied by 2 factorial. So for example, from 1 I go to 4, then 4 to 2, then 2 to 6, 6 to 3, 3 to 5, and 5 to 1. Now this cycle can also be seen as, this is 1 4 2 6 3 5 1. This can also be seen as 1 5 3 6 2 4 1, clockwise and anti-clockwise, and this is why each cycle is counted twice. To have the number of different Hamiltonian cycle, we should divide it by 2. So in case of Kn, it's n factorial instead of 3 factorial, n minus 1 factorial by 2. The only argument which you can think of, that when I started with 1, I could have started with 2, I could have started with 6. It means that there should be 6 factorial choices for the beginning. But in this particular case, when we are forming a cycle, it doesn't matter from where we start. Either you start the cycle with 1 or 5 or 6, this cycle remains same. Therefore, starting point has nothing to do in the number of the different Hamiltonian cycles. How many Hamiltonian cycles are there in this graph? Now you can use the same logic which we have used for the previous question. So this graph is K5. So you fix one of the vertex, and then there are 4 factorial choices. Initially there are 4 choices. Let's say you visit this one, then 3 choices, then 2, and then 1. So in total 4 factorial choices, and each cycle is counted clockwise, anti-clockwise. Therefore 4 factorial by 2, which is 24 by 2, 12. So 12 Hamiltonian cycles are there. Now delete this vertex x and compute the number of spanning trees in the remaining subgraph. After deleting x, you can observe that the remaining graph is K4. Now recall the Calais formula. It says that the number of the spanning trees is n raised to the power n minus 2, and therefore it has 4 raised to the power 2, which is 16 spanning trees. How many of these spanning trees are a part of a Hamiltonian cycle? Now Hamiltonian cycle we have already computed. There are 12 Hamiltonian cycles, and Hamiltonian cycles means C5. Now C5 has degree sequence 2, 2, 2, 2, 2. And with 4 vertices, there are 2 possible spanning trees. One is 3, 1, 1, 1. The other one is 1, 2, 2, 2. Now the spanning trees with degree sequence 3, 1, 1, 1 cannot be a part of Hamiltonian cycle. It means the only spanning trees with degree sequence 1, 2, 2, 1 are the part of the Hamiltonian cycle. You can also observe that each cycle, is these 12 cycles, would have this spanning tree 1, 2, 2, 1. So out of 16, there are 12 spanning trees which are the part of the Hamiltonian cycle, while 4 are there which are not the part of the Hamiltonian cycles. And this is the last one, which says that find a minimum weight spanning tree on the remaining subgraph. So this one is easy. Use Prim's algorithm or Kruskal's algorithm, and after applying it, or even you can directly find it, so you will see that the sum is 19. You can choose 5 with the minimum, then 7 is the next minimum, and then 7, or you can choose 5, 6, 8, or whichever you want. So the answer is 19. That's all from today's class. In the next class, we will discuss some more problem on Hamiltonian graph. Thank you.